All right, let's just dive right into this explainer. Today, we're completely demystifying the complex world of error analysis. Now, if you're gearing up for competitive physics exams, you already know that understanding the actual anatomy of a mistake, it's not just about finding the right answer. It's about securing that ultimate edge over the competition. So, let's get into it. But first, we really have to start by acknowledging a pretty universal truth, one that our source material highlights perfectly. To err is human. Honestly, in physics, it doesn't matter how unbelievably careful you are or how ridiculously advanced your lab equipment is. Making a mistake or, an error in measurement is just an unavoidable human tendency. It's literally woven right into the fabric of experimentation. And that brings up a really fascinating question. Can we ever actually get a 100% perfect measurement? Well, the short answer is no. Actually, not even close. In reality, a totally flawless true value is kind of like a ghost. We can chase it, sure, but we can never fully capture it. There is always going to be some minuscule, microscopic difference between what we measure and absolute reality. So here's how we're breaking this down today. First, the reality of measurement. Then the vocabulary of errors, calculating the error types, when errors combine, and finally, the ultimate power rule. Section 1, the reality of measurement, chasing the true value. Let's look at how physicists actually hunt down this elusive target. Since we know we literally can't get it right on the very first try, what's the game plan? Well, we take multiple shots at it. Step 1, you just take several measurements. We'll call them x1, x2, x3, and so on. Step 2, add them all up. And step 3, simply divide by the total number of attempts. That gives us our mean. In the physics world, this mean value is universally accepted as our absolute closest approximation to the true value. It's the rock-solid foundation that everything else rests on. Section 2, the vocabulary of errors, your gamer's manual. Let's learn the escalating tiers of errors. All right, first up on the list, we have absolute error. This basically tracks the specific mistake of just a single individual measurement. To find it, you take that true value, which remember we just decided is our mean, and you subtract your individual measured value. Now we only care about the sheer magnitude here, so we throw it in absolute brackets to make absolutely sure it stays positive. It's really just the mathematical gap between what you got and the closest version of the truth. But, one isolated absolute error doesn't really give us the whole picture. So we average all those absolute errors together to get the quote-unquote mean absolute error. Once we have that number, we hit our next definition, fractional or relative error. To calculate this guy, you just divide that mean absolute error by your true value. This gives us a much better relative sense of how far off our measurements actually are compared to the overall size of whatever we're measuring. And finally, the big one, percentage error. You literally just take that fractional error we just found and multiply it by 100. That swaps a slightly clunky fraction for a nice clean percentage. And honestly, this is absolutely crucial because it's the most powerful format you'll use for solving advanced problems. Exam setters? Oh, they absolutely love testing you on percentage error. Section 3. Calculating the error types, a real-world example. Let's apply these definitions to a real lab scenario. Okay, imagine we're hanging out in the lab and we're measuring the length of a standard metal rod 5 separate times. Because of our good old unavoidable human error, we end up with slightly different answers every single time. Let's say we get 4.2, 4.5, 4.4, 4.3, and 4.6 centimeters. Now, none of these is the absolute perfect truth, but collectively, they hold the answer. So let's put our steps into action. First, we hunt down the true value by averaging those 5 numbers together, which pops out exactly 4.4 centimeters. Next, we find the absolute error for each individual attempt, just finding the difference between each measurement and that 4.4. Those absolute errors shake out to 0.2, 0.1, 0, 0.1, and 0.2. Then, we average those mistakes together, giving us a mean absolute error of 0.12, which we'll go ahead and round to 0.1 just to match our significant figures. Finally, we divide that 0.1 by our true value of 4.4, multiply by 100, and boom, we discover our final measurement has roughly a 2.2% error. It's incredibly structured, highly logical, and super clear. Section 4. When errors combine, the plot twist of propagation. Now here is where things get a bit wild. The really crucial point is understanding what happens when we start plugging these imperfect, slightly flawed measurements into algebraic equations. This is where errors start to propagate, or spread. And this right here is easily the biggest trap for students. Look at addition, a plus b versus subtraction, A minus B. Your gut instinct might scream that if you're subtracting two quantities, their errors should just subtract two, right? Nope, wrong. The error formula for both of these operations is exactly the same. Seriously, write this golden rule down in big, bold letters. Maximum errors are always added. You can never subtract mistakes. Think about it logically for a second. If you make a mistake measuring a starting value, and then you make another mistake measuring an ending value, those mistakes do not magically cancel each other out to give you a perfect reading. No way. They compound. Your maximum possible error always goes up. So whether you're adding or subtracting the main values, their absolute errors simply must be added together. And you know what? The exact same logic applies to multiplication and division too. Whether you multiply A times B or divide A by B, your errors are still compounding. The only real difference is the format. So instead of adding absolute errors like we did with addition and subtraction, for multiplication and division, you always add their fractional or percentage errors together. Delta x over x equals delta A over A plus delta B over B. You are literally always adding. Section 5. The ultimate power rule, conquering the exams. All right, it is finally time to equip you with the ultimate shortcut. This is the secret weapon that is going to let you conquer those terrifyingly complex exam questions in mere seconds. This is the power rule. If x equals a to the power of p times b to the power of q, all divided by c to the power of r, how in the world do we find the total error? Well, the rule is beautifully simple. You just pull the power down and multiply it by that variable's percentage error. So p times percentage A plus q times percentage B plus r times percentage C. And notice something huge here. Even though C is sitting down there in the denominator, we still add its error. Remember our golden rule? Errors always add up. Let's actually test this out on a real NEET 2019 question. Listen to this incredibly terrifying equation. X equals A squared times B to the half power, all divided by C to the 1/3 power times D cubed. Yikes. And they give us the percentage errors for each variable, 1%, 2%, 3%, and 4%. I want you to try and mentally calculate the total maximum percentage error right now, using that power rule we just learned. Okay, did you get it? Let's check your math. By simply pulling those powers down and multiplying them by the given error percentages, this total nightmare of a physics problem melts right into simple addition. We get 2 times 1% plus a half times 2%, plus a third times 3%, plus 3 times 4%. And that easily simplifies down to 2% plus 1% plus 1% plus 12%, giving us exactly a 16% maximum percentage error. I mean, how incredible is that? What initially looked completely impossible just took a few seconds. Let's lock this new skill in with one more example. This time, it's a JEE Main 2018 problem. Here, we need to find the maximum percentage error in the density of a cube. We're told that the percentage error in its mass is 1.5%, and the percentage error in measuring its length is 1%. Now, quick refresher. Recall that density is mass divided by volume, and the volume of a cube is just its length cubed. So, density equals mass over length cubed. Using our trusty power rule, the total percentage error in density is simply the percentage error of the mass plus 3 times the percentage error of the length. We literally just add the 1.5% mass error to 3 times the 1% length error. That gives us 1.5 plus 3, immediately landing us at a final maximum error of 4.5%. No messy division, no complex derivatives to worry about, just the power rule doing all the heavy lifting for us. Now that you've seen exactly how to turn these dry, intimidating formulas into massively powerful exam shortcuts, my question for you is, how are you going to apply the power rule to your own daily practice problems? Getting super comfortable with this structural approach to errors, it's not just about getting faster at the math. It's really about shifting your entire mindset to realize that even chaotic mistakes follow logical, predictable rules. So go grab a fresh set of practice problems, keep these golden rules in the front of your mind, and start dominating those exams. Thanks so much for joining me for this explainer, and keep on learning.